Hello everyone, welcome to chapter 9. In this chapter we'll talk about alkynes. So in this lecture we'll discuss introduction to alkynes, nomenclature, acidity of alkynes, preparation and reduction of alkynes, and then we'll talk about the reactions in the second lecture. So let's start with alkynes. What are alkynes? Alkynes are the compounds that possess a triple bonded carbon atoms. So these are, you have C triple bonded, and on each side you have an R structure attached to it. So this here is a representation of an alkyne. So alkynes, given the presence of that pi bond, alkynes are generally similar to alkenes because they have the ability to act as a nucleophile. The reason they can act as a nucleophile is because of the presence of an electron-rich region in the center which can act as a nucleophile. So many of the addition reactions of alkene will also work the same with alkynes. So what are the common alkynes that you can find in industry and nature? So acetylene is the common one, that is the simplest of all alkynes, and it's generally commonly used in blowtorches and a precursor for the synthesis of complex alkynes. So more than 1,000 different alkyne natural products have been isolated. So one of them is histrionicotoxin, which is the common compound present in the cigarette. You have an example of a synthetic alkyne is ethinyl estradiol. So this is the active ingredient in many of the birth control pills. And you have, so let's discuss the nomenclature of alkynes and how to name these alkynes. So alkynes are named using the same procedure that we used for alkanes with minor modifications. What are the modifications? First, we identify the parent chain, and remember that it should always include the triple bond. Second, identify and name the substituents. Third, assign a locant, the number, to each, giving the triple bonded carbon the lowest number possible. So we always list the numbered substituents before the parent name in the alphabetical order, and then ignore the prefixes when ordering alphabetically. So the triple bond locant is placed either just before the parent name or just before the "-ine" suffix. So remember the points here. So let's start with an example of how to identify the parent chain. So remember that the parent chain should always contain the triple bond. For example, so here this is pentane, because the double bond is on the edge, so it becomes pentene. If in place of a double bond you have a triple bond is pentyne. Remember that whenever you draw the triple bond, there is no bend, it's always a straight line. So triple bonds are linear structures, remember that principle now. Next you have octane here. So in this structure here, this is the longest chain, but notice that here there is a triple bond here, so which means you have to count from here. So it becomes heptyne. So remember that, you have to remember the structure should always contain the triple bond as the parent chain. Next step is to identify and name the substituents. So in the third step is to assign a locant. How do you assign the number? Always give the triple bond the lowest number possible. Even though the substituents get a larger number, it doesn't matter. Always the triple bond has to be given priority over any other structure. Next, list the numbered substituents before the parent name in the alphabetical order, and ignore prefixes such as iso when ordering alphabetically. So what do you do? So the triple bond here is placed either just before the parent name or just before the "-ine" suffix. So we can name it 1, 2 and 3. You have now on the fifth one there is a methyl group, and a sixth one there is a methyl group, so it becomes 5,5,6 trimethyl, and the double bond is on the second carbon, so it becomes 2-heptyne or hep2-ine, whichever one is the same, so the naming stays the same. Now the common names generally are derived from acetylene, are generally often used as well. For example, if you take acetylene, this is the structure of acetylene, and on one side there is a methyl group, so we write it as methyl acetylene. If you have two diisopropyl groups, so we write diisopropyl acetylene. You have one side you have phenyl group, one side we have a propyl group, so we'll write phenyl propyl acetylene. So remember that acetylene itself is used generally as a side structure. Now alkynes can also be classified as terminal or internal alkynes. So terminal alkynes are the ones where the triple bond is on the edge of the carbon. Internal alkynes are the one where the double bond is inside the structure. Next, let's discuss the acidity of terminal alkynes. So remember that terminal alkynes are generally compounds that have lower pKa. The reason main is because it's more acidic. The reason for acidity comes because of the fact that there is a larger concentration of electrons on one of the structures, which can easily provide more and more chance of getting more and more acidity, because the base becomes really stable, so the acid is going to be really strong. So then other hydrocarbons. So ethane has a pKa of around 50, while ethylene has a pKa around 44, but acetylene has a pKa of around 25. So acetylene is about 19 pKa units more acidic than ethylene, which is about 10 to the power 19 times stronger. Now acetylene can be deprotonated by a strong base to form a conjugate base. We call that the acetylide ion. And we use the ARIO principle to explain why acetylene is a stronger acid. Remember that ethylene, which is stronger than ethane. The reason of that is because of the presence of a lone pair as well as a charge on the negative carbon, as well as the presence of that charge right next to a carbon that is already having a pi bond. And because there are two different pi bonds, again, remember that it's not just one pi bond, there are two pi bonds in one single triple bond. So a general base that has sp3 hybridization is less stable, but an sp hybridized orbital is more stable, which is the common one that we also talked about in ARIO, where the O in ARIO represents the orbital. So the orbital, so the lower the orbital, so the lesser the orbital, the more the stability. So the acetylide ion is generally more stable because the lone pair occupies the sp orbital. Now a base's conjugate acid pKa must generally be greater than 25 for it to deprotonate a terminal alkyne. For example, NaNH2 or sodium amide can easily deprotonate a structure. Now a weaker base such as NaOH can also deprotonate the structure, but remember that here, for it to form a strong acid, for it to be deprotonated, it has to be a really strong base. Now any terminal alkyne can be deprotonated by a suitable base. So when you use a terminal alkyne, it can easily form an alkynide ion. So most commonly used one is sodium amide, is because it generally can be faster and it's the fastest way to deprotonate a general structure. Now these are some of the bases that can deprotonate a terminal alkyne. One of them is, if you take the structure of butoxide ion, you have butylide ion, and you have amine, you have hydride, you have terminal alkyne. So these structures cannot deprotonate. For example, terbutoxide and ethoxide and hydroxide cannot deprotonate a terminal alkyne because they are not stronger to deprotonate the terminal alkyne. So like alkenes can also be prepared by elimination. So, but here, rather than having a single halide, we need to have a structure that has a dihalide to create the elimination process. So when you have a dihalide, that increases the chance. When you have a single halide using a strong base, it can form a double bond, but when you have a dihalide, it can create a triple bond. Now there are two types of halides that can be used here. One of them is geminal halides and vicinal halides. So the mechanism is still the same E2 mechanism, but here when you have a geminal dihalide, the carbon, so one of the carbons contains both the halogens, but in a vicinal dihalide, the halogens are on the adjacent carbons. So in geminal dihalide, the base attacks the alpha proton, removes the alpha proton, thereby releasing the bromine, and then again it undergoes the second reaction further to remove the external presence of another halogen, resulting in the formation. So this is a two-step process when you use a geminal dihalide, but when you use a vicinal dihalide, it undergoes the reaction at once, and this is a concerted mechanism which ends up forming it right away. Now excess equivalents of NaNH2 are generally used to shift the equilibrium towards the elimination product. The reason mainly is because to make sure that the reaction actually forms the alkyne rather than going back to form the dihalide. So we will also need an aqueous workup that is needed necessary to create a neutral alkyne, because remember that NaNH2 can produce alkynide ion, which is generally the structure that forms when you react it with strong bases. Now overall a terminal alkyne is generally prepared when you have a dihalide with excess sodium amide. So remember that whenever you see excess sodium amide, that process will always result in the formation of a terminal alkyne when you have a dihalide. So remember that for this to occur, you need a dihalide and excess NH2. That's when you end up forming the structure. Now catalytic hydrogenation is alkyne is converted to an alkane by the addition of two equivalents of hydrogen. So again, this is catalytic hydrogenation where we use a metal and hydrogen to create the alkane. So we are basically converting an alkyne into an alkane. So the first addition here produces a cis alkene via syn addition, and which then undergoes an addition to yield the alkane. So first it creates a cis alkene which is generally unstable, which under further hydrogenation creates the alkane. Now one way to stop the process to form an alkene is to use a deactivated or a poison catalyst, which can be used to stop the reaction at the cis alkene without further reduction. That poison catalyst is commonly used. One is the Lindlar's catalyst and P2, which is nickel bromide catalyst, nickel bromide complex. So Lindlar catalyst is phenolene with palladium and barium sulfate and methanol. So this entire combined product is called as Lindlar's catalyst, and it is the catalyst that is commonly used to stop the reaction to stop the reaction from further going into form the alkane and stop it to form the cis alkene. So what happens here is that this step undergoes catalysis, but this step does not undergo catalysis, resulting in the formation of a cis alkene. Next, let's talk about reduction of alkynes. So dissolving a metal reduction reduces an alkyne to a trans alkane using the sodium metal and ammonia. So when you use sodium metal and ammonia, this results in the formation of an alkene, but here it creates a trans alkene. Remember this structure, that this creates a trans alkene. This reaction is stereoselective for anti-addition of H and H. Remember that when you use catalytic hydrogenation, it results in the formation of a cis alkene, and when you use dissolving metal reduction, it creates the anti-addition. So we don't need to know the exact mechanism. So remember that know the reagents that are needed to reduce an alkyne to an alkane. So whether it's a cis alkene or a trans alkene. When you use Lindlar's catalyst, you produce a cis alkene, which under further reduction can create an alkane. When you use sodium and ammonia, it can create a trans alkene, which under further reduction also can create the alkane. Next, let's discuss hydrohalogenation of alkynes. So hydrohalogenation is the process where it affords the Markovnikov addition of both hydrogen and the halogen to an alkyne, same as with an alkene. So when you add to an alkene, it undergoes a Markovnikov addition where the more substituted carbon gets the halogen and the less substituted carbon gets the hydrogen. So the addition to an alkyne creates the same process, but it does not result in the formation of an alkane, but it rather creates an alkene. So remember that when you start as an alkene, you end up getting an alkane. When you start with an alkyne, you get an alkene. Now the process, you should not use excess HX, because excess use of hydrohalic acids can create a geminal dihalide where two of these can be added to the structure, resulting in the formation of a geminal dihalide. So hydrohalogenation of alkynes, so the kinetic studies here suggest that the rate law is first order with respect to the alkyne and second order with respect to HX, so which is written as R rate equals to K times concentration of alkyne times concentration of HX squared. So the mechanism must be consistent with a Tummerkiller process, so which involves all the three to be present at the exact same time. So it needs two halogens and the alkyne at the same time for this to undergo the reaction. For each alkyne, you need two different hydrohalic acids to create this structure. Now when you use HBr with peroxides, it generally promotes anti-Markovnikov addition. Remember that it's exactly similar to an alkene. When you use a peroxide, it creates the anti-Markovnikov addition where the bromine adds to the less substituted carbon and the hydrogen adds to the more substituted carbon. This results in the formation of two mixtures, a mixture of E and Z isomers where the bromine creates a trans alkene and a cis alkene, so resulting in the formation of this structure. So this only works with hydrogen bromide, but it does not work with HCl or HI. So we will talk about this mechanism in the next chapter when we talk about radical reactions. So with this, we end our lecture, the first lecture on alkynes.